Good evening and welcome to this week's episode of Science with Maya, Annie, and Dom. In this episode, we will be exploring the astronomical phenomena supernovae. First, we will be answering the question, what are supernovae? Supernovae explosions occur when the core of a star collapses. The gravitational collapse of the core releases enormous amounts of energy. This energy drives the outer layers of the massive star out into space. When the core is collapsing, electrons and protons combine to make a ball of neutrons. Neutrinos are also created as a result of this process. These neutrinos drive a shock wave that propels the outer layers of the star outward at over 10,000 kilometers an hour. This is the explosion defined as a supernova. Next, we will be exploring the two types of supernovae. In their research, scientists have identified two types of supernovae. Type 1 supernovae are white dwarf supernovae, and type 2 supernovae are massive star supernovae. White dwarf supernovae occur when a white dwarf's mass approaches 1.4 times the mass of the Sun. At this point, its temperature rises enough to allow carbon fusion to begin. This happens almost instantaneously throughout the whole white dwarf, creating a carbon bomb detonation. This is similar to the helium flash in low-mass red giants, but releasing far more energy. The white dwarf explodes completely, creating a white dwarf supernova. This is different from the iron catastrophe that leads to a massive star supernova. White dwarf supernova and massive star supernova are differentiated by the type of light that astronomers observe. The luminosity of a white dwarf supernova fades quickly, whereas in massive star supernova, the luminosity decline is more complicated. Additionally, the spectra of white dwarf supernova lacks hydrogen lines because white dwarfs contain very little hydrogen. The spectra of massive star supernova, on the other hand, contains prominent hydrogen lines because high-mass stars contain large quantities of hydrogen in their outer layers. All white dwarf supernovae are very similar in appearance because they always occur when a white dwarf is approaching 1.4 times the mass of the Sun. Massive star supernova, however, all look different because they occur in stars of different masses. After the break, you'll be hearing from Dom on the history of supernovae.
Buy our Milky Way chocolate bars, only $1. Sponsored by NASA.
Around 185 Common Era, Chinese astronomers recorded observations of a supernova, and again in 393 Common Era, Chinese astronomers again recorded observations of supernova. Later, in 1006 Common Era, astronomers in China, Egypt, Iraq, Italy, and Japan observed and recorded supernova 1006. And later, in 1054 Common Era, Chinese, Japanese, and Arab astronomers observed supernova 1054. It's also been noted that Bra observed supernova during his lifetime. Despite the many supernova observations, very little was known about supernova until recently. The most recent to be seen supernova in the Milky Way was on October 9th, 1904, and the observed supernova was supernova 1604. Although the true nature of supernova remained obscure for some time, in 1931, the word supernova was first used in a lecture, and later in 1938, supernova gained more momentum in the scientific community when Walter Baade was the first astronomer to identify a nebula as a supernova remnant. And finally, in 1941, Rudolf Minkowski performed the first spectral evaluation of a supernova. He proposed a type 1, 2, 3, and 4 classification system for the supernova. An interesting fact is that no supernova has been observed in the Milky Way since 1604. In 2003, supernova 2003 FG was observed and was massive enough to challenge the Chandrasekhar limit. On May 21st, 2008, astronomers caught a supernova on camera right before explosion. This was the first image of its kind. And with the development of neutrino detectors, we are sure that we will catch all supernovas in the future.
A supernova remnant is the structure resulting from the explosion of a star. Supernova remnants consist of ejected material from the explosion and the interstellar material it sweeps up along the way. Supernova remnants go through 5 stages of expansion. First, the ejected material expands freely until it sweeps up its weight in interstellar material. This stage can last anywhere between tens of years and hundreds of years, depending on the density of the surrounding gas. Next, the supernova cloud sweeps up a shell of shocked circumstellar and interstellar gas. Strong X-ray emission traces the shock waves and hot shocked gas. Third, the swept-up circumstellar and interstellar gas cools to form a thin, dense shell around the hot interior. The shell can be clearly seen in optical emission from recombining ionized hydrogen and ionized oxygen. The dense shell continues to expand by momentum. This stage is best observed from the radio emission of neutral hydrogen atoms. The final stage is merging with the surrounding interstellar medium. This occurs roughly 30,000 years after the initial explosion, when supernova remnants slow to the speed of surrounding interstellar medium. It merges into the general turbulent flow, contributing its remaining kinetic energy to the turbulence.
So the degeneracy pressure that briefly supports the inert iron core of a star arises because the law of quantum mechanics prohibits electrons from getting too close, and gravity pushes these electrons past the quantum mechanical limit, and then these electrons combine with protons to form neutrons, and in this process neutrinos are released. The explosion happens in a fraction of a second, but in this fraction of a second, a star the size of our sun or much, much larger can collapse into a ball of neutrons a few kilometers across. The outer layers are driven off into space, and this explosion manifests as the supernova. A supernova can have the luminosity of a medium-sized galaxy and the brightness of 10 billion suns for about a week. The collapse of a star releases a ton of energy, more than 100 times what the sun will radiate in its lifetime. Additionally, the neutrinos released in the process can travel from the sun to Earth in only 4 hours as they move at about 10,000 kilometers per second. Scattered debris from a supernova carries elements off, and millions or billions of years later, this debris could partially compose a new generation of stars. It's the star stuff that Carl Sagan always talks about. Finally, in the R process, heavy nuclei are bombarded with large neutron flux to form unstable neutron-rich nuclei, which undergo rapid beta decay and form more stable nuclei with a higher atomic number. The end result is neutron-rich heavy isotopes, which are released.
Hey there, this is Annie, and I'm here to talk about the effect on surrounding space. Firstly, supernovas create shock fronts, which are a wall of fast-moving, hot ionized gas at its edge. This heats, compresses, and ionizes all the gas that it passes in the surrounding area. Sometimes this results in new stars being formed. Gas will cool down as the supernova remnant gets older due to diffused energy. These shock fronts and the supernova explosion clean out the surrounding space material with it. It can carry up to 45 solar masses. Secondly, supernovas create the universe's heavier elements, iron and heavier. These elements enrich the surrounding gas, and the stars that eventually result from these gases' compression will integrate these heavier elements into its makeup and the solar system. This is what gave rise to life on Earth. Another effect of supernovas are the cosmic rays that are sent out from them. These can cause genetic mutations in living organisms. It is found on average that one cosmic ray particle will hit your body per second on Earth. These rays are made up of protons, electrons, and atomic nuclei. My last point is supernovae bubbles. These recycle matter in the galaxy. These bubbles are gas that is ejected at high speeds from the supernova, or are intense stellar winds that sweep up material in the surrounding interstellar area, creating a bubble of hot ionized gas. That is gas where its atoms have been stripped of their electrons. These aren't always easy to detect and are only evident through radio emissions of the shell of gas around them. Fast fact, we live inside one of these bubbles. Okay. These bubbles can grow up to 100 light years across before merging with the surrounding interstellar environment. Some bubbles, however, combine to make superbubbles, observed up to several thousand light years across. Shock fronts of these bubbles can combine their energies to make a super shock front. If a superbubble breaks away from the Milky Way disk, it results in what is called a blowout, where the hot gas erupts like a volcano out of the disk and shoots upward into the galactic halo with only gravity to slow it down. A galactic fountain model shows the slowing and cooling of the blowout. The resulting cooled gas farther away from the disk will, by gravity, rain back down into the disk and merge with the rest of the galactic material. If this model proves true, it is incredibly important in terms of galactic recycling. However, it is somewhat difficult to verify.